All right, so we're starting the second half of our electric force, field, and potential unit, and the first section in it is electric potential and potential difference. So right now we've got a diagram here where there's a positive plate and a negative plate, and I've put a couple of positive charges and a couple of negative charges on there. First thing I want you to think about is what direction is the electric field going to flow? If you remember, electric fields always flow from positive to negative because they show the direction a positive charge would go. So our electric field would look something like this. There we go. As we go towards the side, it'll be straight the whole way through because these plates are straight. They're parallel with each other. When we get to the edge, it would kind of bow around the sides, but we won't worry about that because our particles are all inside of the plates. What I want you guys to do is fill out this chart for our positive charges and for our negative charges. So for the positives and the negatives, I want you to tell me where they have the most potential energy, where they have the least potential energy, where work is going to be done by the electric field, and where work is going to be done by an external force to make it move. So this would be like where you have to push against the electric field to make it happen. So I want you to take a second, pause the video, and tell me about when it'll be what. And let's call this plate A and this plate B. So tell me when you're at A, at B, when you go from A to B. Go ahead and fill out the chart, and we'll be right back in just a second to go over it. So let's take a look here. Our positive charge and negative charge are basically just mirror images of each other. You notice that when a positive charge is at the positive, at point A, that's when it's going to have its most potential energy. When it gets down to the other side, it's at the negative. It can't move anymore. It's where it wants to be, so it'll have its least potential energy. The inverse is true for the negative. The electric field wants to do work on a positive that's near positives. It wants to push it away. It's the direction that positive charges want to go. So it's going to be work by the electric field when you go from A to B. But when you have to go from B to A, you're going to need an external force to do that work. The opposite is true for negatives. While we're on the topic of work, how do we find out work done by an electric field? So this is work by an electric field. We should remember that work is force times distance. And if we're working backwards from electric field, we know that electric field is equal to electric force over the charge. I'll make a little e there to let you know it's electric force. So when we combine those together, what we get is or not yet, we're just solving for electric force. We can now plug this in over here. And when we do that, we get that work is equal to electric field times the charge of the particle in it by how far it travels in the electric field. You can also write it QED, whatever order you like them in. Next up, we're going to talk about electric potential. So what is electric potential? What's electric potential? It is electric potential energy divided by the charge. So this is the potential energy of something with charge divided by how much charge it has. And this is basically the same thing as what we call voltage. So how do we write that out? V is equal to your electric potential energy divided by your charge. You can also see it written as change in voltage is going to be equal to your change in electric potential energy divided by your charge. So when we plug it in with work, what we're going to get is work is just equal to your negative change in electric potential energy. Remember, the amount of work done by the electric field is going to be equal to how much the electric field has moved it, how much energy it's used in moving it. So it should just be the negative amount of that. Before I move on to that, we can also write this as electric field times the distance. And the reason that we can get that is from down here, that work is equal to Q ED, which is going to be equal to VQ when we rearrange this. So charges cancel out, and what we're left with is that voltage is equal to your electric field times the distance that it travels over. So what is this saying? Basically, the further you travel in an electric field for a given charge, the more your voltage is going to drop. Doesn't matter what your charge is, because it's just how you're traveling through the electric field. Your potential energy is going to have to do with how much your charge is, but voltage is independent of charge as long as you have one. So let's try a little application with this. We've got an electron that's traveling in between two plates. We've got a high voltage on this side, a low voltage on this side. Our high voltage and low voltage both have an absolute value of 2,500 volts, but our low voltage is negative. I want you guys to answer these three questions. First one, which plate does the electron move towards as it travels through here? Imagine it's moving downward. Then for the second one, if it starts over here near the negative plate, what is the change in potential energy that's going to happen as it travels from one plate to the other? And then for part C, if we started it from rest near the plate, which it says in this part, if we started it from rest, what is its final velocity going to be? So I want you to go ahead, use the equations we just learned, attempt it, and then in just a few seconds we'll be back together to go over it. Okay, let's see how you did. Hopefully the first part was easy. You know an electron's negative. Negatives are repelled by negatives and attracted to positives, so it should go down to the positive plate. Next up, if it starts at the negative plate, what is its change in potential energy from start to finish? Well, if it starts over here and it goes over here, that means it's going to go across a 5,000 volt difference. Remember, electrons, electrons are always going to go the opposite direction of what an electric field does, because remember, an electric field shows where positive charges want to go. So an electron's going to go from here to here. If we use our equation that our change in voltage is equal to our change in electric potential energy over the charge, we can rearrange it to solve for our change in electric potential energy. We take our final voltage, positive, minus our negative voltage, so we add it. We get 5,000 volts times the charge of an electron, and we end up with the change in potential energy of negative 8 times 10 to the negative 16th joules. The reason for that being that it is losing potential energy, so it should be a negative number. Then we know that that amount of potential energy that it lost is being converted into something else. Obviously, in this case, it's going to be kinetic energy. So we can set our change in potential energy equal to our change in kinetic energy being 1/2 mv squared. And what we do is we just plug in the value there, set it equal to 1/2 the mass of an electron. Dang boy, that's a tiny boy. And then solve for the square of velocity, then take a square root. When we get there, we find that our velocity is going to be 4.2 times 10 to the 7th meters per second. That's a spicy meatball. And that's all we have for this section of notes.